G'day lads, it's my first year 12 math video, and it's not a particularly easy one to do. I've done a few real simple algebra ones for my year 9s this morning, and I've walked my year 13s through a calculus problem today online, and that was all really cool. But today I'm going to be talking about degrees and radians, specifically the conversion between the two. So I think in class I asked you guys where did the 360 degrees come from, and so it was created by the Babylonians 2,500 years ago, and it's loosely connected to the number of days in a year, 365. But the other really important thing about that number is that it's based on what is called a sexagesimal. Yep, that's spelt correctly. Sexagesimal, which means I think that means base 60. So in a clock, base 60, where you go 60 and then you start again, 60, start again. So it's all that similar concept. So 360 closely linked to the number of days in a year, but also this number can be divided into a hell of a lot of different segments. You've got 1, 2, 3, 4, 5, 6, 8, 9. You got 12 and 18 and you got 20. I could go on for quite a few numbers. The only other number that I can think of with the most factors is 840, or 3-digit number with the most factors. So some mathematician a long time ago came up with 360 degrees because it was a convenient number to divide a circle into. What I'm going to do now is I'm going to define a radian. And you guys are giving me some answers online. They're all really good. So a radian kind of looks like this, where if that's the radius and that's the radius, if we have this as part of a circle and this is also the radius, so all three of these sides are the same, but this is the arc of a circle, then this angle is what we call a radian. So there's 1 radian. And I'm going to ask how many radians would fit into this circle. So what I've done is, I probably should have made this a little bit bigger, but I've gone and got myself a radius piece of string. Okay, so I've got a radius length here. Now if I curve that along the edge of this circle, so if I just place it on there like that, okay, then that's about 1 radian, because that's a radius, and this is a radius. So I might actually just pop that on there. So that is 1 radian. So how many radians in a full circle? Well, if I go around to here, right, I put that on there, then that is going to be another radian. So that's going to be another radian around there. Excuse the y-axis. So I've got 1, 2, and I could do it again. And I've got 3 going to there. Interesting. So I've got 3 radians going all the way around there, where this length is this length, is this length, is this length, and each of those is also the same length. And it's, I think to some of you it might be really obvious, but we didn't quite get all the way around to there. We've got this little bit left over in here, right? We've got this little bit left over. And so what that equates to is about 0.14, okay? 1459, whatever that is. So to do half a turn, we say that is pi radians. 1, 2, 3.14 radians fit half a circle. And so if I was to go a full turn, if I was to turn something all the way around, this would be at 2 pi. So what we can say is that 0 degrees, a 0 degree turn, so that would be here, that's not turning, we can say that's 0 radians. But it's also the equivalent of turning all the way around and going around 2 pi. Alright, so a full turn could also be written as 2 pi. So 360 degrees is 2 pi radians. Right, I'd get 6.28 of these radians all the way around. Nice. And so that's why the circumference of this, if this is our radius, we can get 1, 2, 3, 4, 5, 6 and a bit radiuses around the outside, and that is why circumference is 2 pi times the radius, because I have 2 pi radiuses around the outside. That's where that formula has come from. So what I've got is I've got a partially filled out table here, and we're just going to look at roughly how many degrees and radians each of these are. So if I got pi over 4, start with this one, if I've got pi over 4, well that's pi over 2, isn't it? That's halfway to pi, it's pi divided by 2. If I divide that by 2, I get pi over 4. So how many degrees would that be? If you thought 45 degrees, you would be correct. What about going back the other way? What about 60 degrees? Well, 60 degrees is about up there, like that, and that's about a third of the way to 180, isn't it? Well, it is. 60 degrees is 1/3 of the way to 180. So this would be a pi radians divided by 3. Okay, and I said before that halfway to pi, or pi divided by 2, well that's a 90-degree turn, isn't it? That's just turning perpendicular to your original orientation, so that's 90 degrees. 2 pi divided by 3, well it's a third of the way to 2 pi, and actually what that comes out to be is that's 2 lots of pi over 3, isn't it? So I'm at 120 degrees. That's pointing about there. 2 pi over 3, 2/3 of pi. So 180 degrees is pi radians, that's this way. And so 270, well that's 3/4 of the way to 2 pi. So 3/4 of 2 pi, or you can think about it as pi and a half, right? Pi and a half, so 3 pi over 2, because you know that 3 over 2 is 1.5. So in a way, the pi just becomes a unit of measurement around the circle. And this is really powerful because all based on the actual geometry of the circle, not what someone created, but actually has a pure relationship with the geometry of the circle. 36 degrees is an interesting one. That you would find is pi over 5. Right, it's 1/5 of the way to pi. Pi divided by 5. 180 divided by 5 is 36. And I've just put this example in as well because that's, I've said it before in numerous lessons, is there's nothing better than fractions. Nothing is more accurate than a fraction, and pi over 8 illustrates this quite well. I could have said that that's 22.5 degrees, but it's a lot nicer to say that that was pi radians over 8, or 1/8 of half a circle. So 2 really key aspects come up. It's this one. 180 degrees is pi, which means that 1 degree is pi divided by 180. 1 degree is pi over 180. And you can see that there. So that means that we can now have a conversion. So if I had 180 degrees, 1 degree, one of those is pi over 180. That's what that is meaning there. So we have one conversion of measurement there, and if I have pi radians, well, we said that pi radians is 180 degrees, and so now we can do conversion. So if you want to copy that into your record of learning, maybe highlight the little extra there and put the pi radians in. That would be a nice record of learning. So you could pause that there and copy that down. What we're going to look at now is conversion. So what we can do is we're going to be converting. So hopefully I've got that lined up with the camera. We're going to convert. So what did I say before on the previous page? It was 1 degree. It's pi over 180. Right, so that was simple. It was pi. Halfway around a circle, divide by the number of degrees. And we have pi radians equal to 180 degrees. So let's convert 45 degrees to radians. Well, you guys should pause and give that a go, but we did discuss it before. We could just go, for every one of these degrees, we have pi over 180. So we could just go and say that 45 degrees is 45 lots of pi over 180. And we always leave it in terms of pi. So that's 45 over 180 pi, and 45 over 180, you guys know that simplifies down to 1/4 of pi, and we leave it in terms of pi. So it's pi over 4. It's as simple as that. For every degree, you just need to times by pi over 180, and that's how you get your radian measure. It's really easy, right? Just times by pi over 180. Going back the other way, let's have a look. Convert, let's have a look, 2 pi over 3 to degrees. Well, you could possibly divide, right? Just do the inverse. But what we have is that every pi radian is 180 degrees. So all we have to do is go 2 and replace that pi with 180. So 2 times 180 over 3, and that's 360 over 3, 120 degrees, and it's that easy. Right, there's my conversion there. That pi we know is equal to 180 degrees, and so we just substitute it in and things fall out. For degrees to radians, for every one of these, we know pi over 180 is equivalent to 1 degree. So that's really, really nice. What we're going to look at now also, as I know this might be a wee bit of a long video, but again, you can pause and just come back to a lot of this stuff. We're going to look at the arc length. So if I wanted to know the arc length of this thing, right? And we're going to do this in radians. So we're going to say that this is 8 centimeters, 8 centimeters. So it's just part of a circle. And I want to know this length here. Let's call it S. Okay. Well, we know that the arc length, S, so arc length is actually proportional to the radius times by the angle. So I haven't actually put the angle in, have I? So that's 4 pi over 5, let's say. You guys might want to just convert that to degrees, see what that is. But if I was going to get that, then the arc length is actually equal to the radius times the angle. That's why this radian measure is so nice. Arc length is just radius times the angle in radians. So this S is traditionally used for S for arc length. So S equals 8 times 4 pi over 5. And what you get is you get 32 pi over 5 centimeters. What does that look like as a decimal? If we just go on our calculator, you don't need to be in radian measure or anything because all we're doing is pi. That's 32 times pi divided by 5, 20.1 centimeters. 20.1 centimeters. So now we can find the arc length. Now if that was given in degrees, you just have to come back to this and do a conversion. So let's have a look at what that might look like. So let's say we had, let's do something quite similar. Let's just go 100 degrees, okay? And that was 10, and that was 10. Let's go meters. And we want to know this length here. Okay, so we could call that x, we call it anything. Well, we know that the arc length, x, is r times theta, but only in radians. So we need to convert this to radians. And we know that 1 degree is equal to pi over 180. And so 100 degrees is 100 pi over 180, and 100 over 180, that symbolizes the 50 over 90, or 5 pi over 9. It's pretty traditional to simplify your pi radians down as far as you can. And now we can find the arc length. There's just going to be 10 meters multiplied by 5 pi over 9. Let's have a look at that. So 10 times 5 pi divided by 9. So arc length is 17 point, we're going to call that 5 meters. So if it's in degrees, you just have to make a quick conversion, and then you can plug it into this really nice formula. And this formula, arc length, S equals r theta. Note that that's radians, is one of the 7 formulas you will need for your internal. Awesome. Well, I'll leave you with that. I'll assign some work to do on arc length, which could be really cool, and I might just make a video running through a couple of other problems. I'll see how I go today, but I'll make that available in the morning. Like that smash button.